Hello everyone and welcome back. I'm Mr. Cobalt, and in this video we're going to talk about mixtures of gases and partial pressures. So one of the things that we need to keep in mind is when we're talking about ideal gases, there's some characteristics of ideal gases or assumptions about them that we make. The one assumption is that we assume that there are no interactions between the particles. And so what that means is that if you have a mixture of gases, then the gases are going to behave as if they're all by themselves, right? So one gas is not going to interfere with with another gas. So the particles of one gas are not going to interfere with the particles of another gas. So in that case, if we're assuming ideal gases, then we can kind of view them by themselves, and we can think of them as being separate from each other. So if you have a mixture of gases, then you can look at and figure out what the partial pressure or what the pressure of that particular gas in the mixture is, if you know the moles and the conditions of the gas, like pressure, temperature, and things like that. So if you know the number of moles, and you know the temperature and the volume, and of course you know R, then you could figure out the pressure of that gas by itself without having to worry about what the other gas molecules are doing in the mixture. And so this is, and you could do that for each and every gas in the mixture. And so you can see this here. So we have the ideal gas law here, and it is solved for pressure, and N represents the gas that we're looking at. So the pressure of the gas is equal to whatever moles of that gas we have, and then multiplied by R, multiplied by T, the temperature in Kelvin, and divided by the volume in liters. And so when we find the pressure of a particular gas in a mixture, that is called the partial pressure. So the partial pressure is the pressure due to any component of a mixture of gases. So here's an example. So if I have a mixture of gases, gas A plus gas B plus gas C and so on, then I can figure out the partial pressure or the pressure due to that component, like A. So if I want to find the pressure of A, then this would be the pressure of A equals the moles of A multiplied by R, and the temperature and the volume. And so since all the gases are in a mixture, then they must all be under the same conditions, right? So same temperature for all the gases in the mixture, same volume, and so on. So the R, T, and V are going to be the same for all the gases. The only difference is going to be the number of moles of gas. So for this would be PA is the partial pressure due to gas A. And that's the number of moles of A multiplied by RT divided by V. And for gas B, it'd be the moles of B multiplied by R and T and divided by V again, and then so on for gas C. So the number of moles of C multiplied by R, T over V, and so on. And so you can calculate the partial pressure of each gas in a mixture if you know the number of moles, as well as the other conditions, temperature, volume, and of course R. And the great thing is that the total pressure of the mixture is going to equal the partial pressures of the individual gases. And this is called Dalton's law of partial pressures. Oops. So Dalton's law of partial pressure says that the total pressure of a mixture of gas is going to be the individual partial pressures of each component of the gas added together. That's the Dalton's law of partial pressures. So we can go on and say, okay, if the partial pressure of A plus B plus C equals the total, then if we know that the partial pressure of A is equal to this, then we can substitute PA for this, the number of moles, plus PB, the partial pressure of B, with NB, RT over V, and so on. And then since RT over V is the same for all of them because they're in the same container, the same volume, same temperature, pull that out and it's going to be the number of moles of A plus B plus C. And so then the total pressure is going to be equal to the total moles of multiplied by RT over V. So we can use that equation as well. So the total pressure is going to be equal to the total moles multiplied by R times T divided by V. Now that we have this equation and we have these equations here, so we have the partial pressure equation and we have total pressure equation. What happens when we divide these? So I'm going to go over here. So if I take the pressure of A, right, let's take A. The partial pressure of A is equal to the moles of A times RT over V. And let's say I divide that by the total, right? So total pressure is equal to the total moles, also multiplied by RT over V. So if we divide those equations, then the RT over V is going to cancel out. And then what you're left with is a fraction equal to a fraction. So what you end up with is PA, the partial pressure of A, divided by the total is going to be equal to the number of moles of A divided by the total moles. And so this is going to be very important because what we call this, so this is going to be moles of your gas A divided by the total moles. We're going to call that's going to be the mole fraction. So that's referred to as the mole fraction. So N, the moles of A divided by the total moles, that's going to be called the mole fraction, and we represent that by a chi, Greek symbol chi, which looks like a funny X, and that's going to be A. So this is the mole fraction of A. So the how many moles of A per total moles. And the thing is, if NA, if the number of moles of A over the total moles is equal to the pressure of A over the total pressure, and this is the mole fraction, then the pressure of A over total pressure is also equal to the mole fraction, right? So both of these are equal to each other. This one is equal to the mole fraction, so therefore this one is also equal to the mole fraction. Now, if we put this together, what you'll see is, so we have the pressure of A over the total pressure is equal to, that's going to be equal to this, but that's also equal to, that's called the mole fraction, so the mole fraction of A, right? And so now if we kind of manipulate this a little bit, we multiply both sides by the total pressure, right? Multiply everything by the total pressure. So that's going to cancel out. So then what we get is the pressure of A, the partial pressure of A is going to be equal to the mole fraction with regard to A. So the number of moles of A divided by the total moles times the total pressure. So this is going to be a very useful equation. So if you know the mole fraction and you know the partial pressure or the total pressure, you can find the partial pressure of A with this equation. And so also keep in mind that partial pressure of A over total pressure of A is equal to the mole fraction. And this is what we mean by mole fraction. So if they give you moles of A and the total moles, or if you can calculate the total moles, then you can find the mole fraction. Okay? And so this is going to be useful. Dalton's law of partial pressure is going to be useful. The total pressure is equal to the partial pressures of the gases. And again, you can find the partial pressures of the gases using the ideal gas law as well. So there's a lot here that is going to be useful when we're talking about partial pressures and mole ratios and things like that, when we're talking about mixtures of gases. Okay, so I hope this is helpful. If you like this video, like it, share it with your friends, make a comment in the comment section. Let me know what you think. Subscribe to the, ring the bell, subscribe to the channel, and thank you for joining me, and I'll see you next time.